Hi, good morning, everyone. Hopefully, you can hear me. Yeah, it shows some sign that the audio is working and video is on. We can get started. 20 people, that's good news. So about time we get started for today and go through the course. So this is Ali Rasek. I'm a structural engineer with HDR, and I'm teaching earthquake engineering course at University of Victoria. Now the picture looks okay. I think we're in good shape. In terms of module, yeah, we are somewhere here. We are still working on the National Building Code of Canada between 6 and 7. And that's the two most important modules of the course. So it's okay if we are slightly delayed. In terms of scheduling, we are already into July, and yeah, in terms of timing, yeah, we are delayed, but I will do some other parts faster as if it's a conference, but I don't mind to spend time on National Building Code of Canada. Besides, like these two sessions won't be as busy as I initially estimated. I talked to Benham Siler. I mean, probably mostly my fault. I didn't chase marking your draft reports soon enough. I got carried away by the end of week, long weekend, vacation, and etc. And now we are slightly behind. I try my best to give you feedback on the draft report by Monday. However, as it would be already late for your July 19 deadline. No, sorry, July 12 deadline. Yeah, so here we said your deadline is July 12. We give you 1 week to apply the comments that we give you. So for now, I extend the final report deadline to July 15. And yeah, tell me if it doesn't look okay, etc. Let me know. Otherwise, I can note it here. And I will send an email as well. This new version is different. So extend to July 15. So right now the plan is that I give you feedback while you are working on your final report, because there's a lot of things that you guys know that you should improve. You already know that you should progress. I give you feedback by July 8th, and then you have 1 week to complete the report. So we will get the, yeah, so that's the deal right now. And yeah, there's a chat. With the presentation slides, yeah, we will think about it when we get there. Yeah, it's not like my main intention is that everybody has equal amount of time to work on things. But if all teams, even say, I'm not writing it now, but even if all teams provide presentation slides by July 26th or July 25th, then everybody has equal chance. So that's the final intention, that everything is equal. So I hope I answered your question. Yeah, I will think about it. We will decide about it maybe about next week, but it's very possible. Yeah, but Alvin, we can write it now. So for now, we say thinking that maybe we will change it one more time, but for now we say extended to July 22. So 1 week after so that you also have a weekend. Sometimes some students, or even myself, sometimes I have easier time doing some stuff in the weekend. So for now, we extended both of them. Yeah, but the ultimate goal is that really by 25th, everything is ready so that everybody has equal opportunity. Then some teams will present on 26th and some teams on August 2nd. Oh yeah, right now we have only like 7 teams. We can even do it in one longer session. And then I can teach in the other session, but I didn't make that decision. General form of the outline will remain the same. Yeah, scoring remains the same. Yeah, some questions came up about class presence and quiz. Yeah, as I said, like I emailed back one team saying that as long as I see class presence order of 25, which is not today we have only 21, I don't feel urgency for checking class presence, but now I'm feeling it slightly. So 21 is not yet 25. Maybe some people join us in a few minutes. And quiz, yeah. So eventually we should somehow like make up this 20%, although I'm not a quiz giving person, but I have to do it. I committed to it now. I will inform you like maybe next session, next Tuesday, I will email you on Monday and say tomorrow we have a quiz. And by quiz, what we mean is that it will be a simple question, completely fine to check your books and notes and Google search, ChatGPT, etc. But however, I like you guys not to talk to each other. So you should do it independently. It's not intended to be a difficult, in-depth question. That part you are tested through your reports that you have in-depth knowledge, and you will present to prove that you have in-depth knowledge. The quiz is just generally, I get a feeling that you are listening, etc. So it will be easy. You are allowed to, it's a short one. You can open book, etc. Even internet search. But yeah, like, no, don't talk to each other. So don't text message each other. Do it everybody on his own or on her own. So most probably you receive an email from me. So I will give you heads up as well. I think yeah, somebody mentioned that I should give heads up because some people prefer to study or at least print their slideshows, etc. So that's fine. I will give you heads up, but it's not today. And that's also, I have a second reason for that because yeah, like on Monday, I will tell you there's a quiz and hopefully more than 25 people will show up. That's it. Hopefully I answered you, Jap chat, and I can proceed with the course. Yeah, let me see where we can continue from. I remember that we went through this one, accidental torsion. Yeah, I highly recommend. Yeah, we were at the modern design philosophy. I don't mind to go through this one more time. Yeah, I highly recommend that you guys really learn and review at least the slideshows for NBCC. So just go through them a few times, practice, etc. I understand that maybe some people say I am not too interested in dynamics of the structures, etc. But because you are taking this course, you should really be fluent with design philosophy, high level for all codes, and also what the National Building Code of Canada asks us to do. So yeah, so we at this point we explained the details for using the National Building Code of Canada procedure, the equivalent static method, distribution of the load between different floors, seismic load, how to modify for higher modes, which meant increasing the base shear and reducing the overturning moment. We went through those processes. And yeah, I urge that you guys more deeply learn that than other sections. And now we go higher level, and this is just generally what every code in the world think about when they are discussing the design philosophy. This has been popular maybe in the past 50 years or so, this using the design spectrum, etc. So that's modern seismic design philosophy, which is successful as well. Like the quality of design has been improving all the time. So this is a good knowledge to have as a seismic structural engineer. How design a standard design spectrum, we know how to read it from the NBCC related website. So this is the general concept for most codes. The design spectrum has a flat section and also a curve section, or in Canadian case, it will look more like a multi-line, but which is the same thing, same outcome. So there is like, it's like you can think about this curve shape, which is capped by some value. And the cap is proportional to the peak ground acceleration. And the curved one has a reverse relation with period. For very long periods, the US codes ask to use another curve, which is like has a reverse relation with t to the power of 2. So that's the general idea here. And the codes, all the codes, most of the codes that use this philosophy, they will guide you on how to build this curve. And then given t, a spectral acceleration is read using this curve. So you know the primary period of your structure, either by a simple analysis or by, again, most codes have recommendations on how to estimate the period. And then you can read the spectral acceleration, which is the most important. Spectral displacement and the spectral velocity are also important, and they have relation with a spectral acceleration. You can determine those as well. So that's the general procedure that is repeated in every code around the world on seismic design. Another important part of the design, another notion that we should always be aware of, and in every code you should look for these concepts, including the Canadian code, is that there is a elastic demand spectrum that the code guides you to basically build. And it's like, what if the structure remains completely elastic with 5% damping throughout the earthquake? And then the code gives you a reduction factor to reduce it. Sometimes we don't build this second curve, which is called elastic design spectrum, because although the nonlinearity is accounted for here, but you use the elastic results to elastic stresses or elastic forces while you are using this curve. So there's elastic remains elastic because when you use this curve and you determine the forces, you apply those forces on the elastic model of the structure. However, the nonlinearities and ductilities are accounted for by this reduction factor. Most of the time, we don't really build this. We build the higher one. We determine the SAE, and then we use the modification factor or reduction factors, such as what I showed you in the Canadian code, to reduce SAE to SAD. And there are like unique features of seismic demand, which is the cyclic behavior and its short duration bursts with high frequency, and the fact that it's not harmonic, it doesn't exactly repeat itself, although it's cyclic, but it's not harmonic. those features of seismic demand has resulted in the codes adopting this solution. So that those are the features, like you don't have a similar concept for wind, because wind is not really cyclic, it's slightly cyclic, but the gust might be like longer duration than like earthquake reaches its maximum value in milliseconds, but the wind gust might have a longer duration. So this, we don't have similar philosophy for wind, although we think that both of them are lateral load. We don't have similar philosophy for wind because wind doesn't have similar nature as earthquake. Going to the next one, just reviewing the two reasons we use for that ratio, that modification ratio, that like instead of using SAE to determine the load, we reduce it to SAD. And then Canadian code, they are separated. So one feature is that because the structures becomes nonlinear, ductile, therefore the demand reduces. Like the structure doesn't remain as stiff, therefore it won't have as much demand. And the second feature is the overstrength. Like while we try to design our structure for this capacity, we are really designing for this capacity. So the overstrength factor also comes in, and therefore the combination of these two features is where we reduce the demand on the structure. One step from SAE to SAU to account for the activity, and another step from SAU to SAD to account for overstrength. So that's the basis for seismic design philosophy in a way. The ratio of elastic response to a spectrum for elastic design, I don't know if I said response as a design, is typically between 4 to 8. So between the ratio of SAE to SAD is between 4 to 8. In US code, normally they give you one value for reduction factor. In Canadian code, they have basically, they have basically two portions, and they should be multiplied to each other by each other because of that's the rationale for that. So one part because the demand really reduces, and one part because the capacity is more than what we estimated. Next one, so re-emphasizing the importance of ductility, performance benefits of inelastic deformation. It dissipates energy, it protects non-ductile elements, and it redistributes loads. When one member slightly weakens because of ductility, another member takes on the load. That's what is called redistribution. And the dynamic characteristics also changes. The period normally increases, and in most cases, increase in period means a reduction in demand. Like you see these curves like this. So when like this reduction is partially because the period has increased, and when the period increases, you go down on this curve. So that's part of the benefit of ductility, besides the fact that it dissipates energy. So altering dynamic characteristics is beneficial to us. And this is like like normally we think about the steel when we see this curve, and that's the way a steel behaves. It yields, and then during its deformation, it keeps on dissipating energy. While if you have a member which doesn't yield, um, energy dissipation is low and there's a higher force and the period doesn't reduce. For concrete, by nature, it's more like uh, not showing ductility, but by providing proper detailing and reinforcing, we push it to behave more like a steel. Like a steel is like our poster child and the ultimate ideal for structural design, and we try to make concrete behave the same or even wood behave the same. So make them act more ductile by proper detailing and connections and etc. Or use of steel basically within them. We talked about the response spectrum curves, the real response spectrum curve, which looks like this crooked, and one that you prepare using the code, which is a design spectrum, which is a few flat lines in Canadian case, or in most other codes, a flat part and a curved part, which mimics basically the real spectrum. And the fact that re-emphasizing that even in real case, when the structure softens and the period increases, we have lower demand. So the elastic structure had a period of T prime, but it softened because it yielded. The period increased to T prime prime, and therefore the demand is less. As one like important top concepts in any code, any modern earthquake code. The capacity protection idea, as we emphasized a few times, is based on the idea that in the load path of the system, carrying the lateral load from top to earth, there are quite a few non-ductile members, such as in this case, the diaphragm and the connections, and more connections, maybe doubling down, etc. Foundation itself, all of them are non-ductile. And we want to have at least one ductile member in between as part of the chain that carries the force to the ground. And we need to capacity protect every other member because like we want the ductile member to be, we call it weak link. We want the ductile member to fail in case of emergency, in case of earthquake. We want the ductile member be the one that fails because other members will have a brittle failure. We don't like it. It's like sudden failure. The structure might collapse and has more damage to life and to economic losses as well. But when the ductile member, in this case, this bracing starts failing, it elongates and basically at least give the occupants a chance to run away. So the whole philosophy behind capacity protection is that don't allow other members to fail before your frame, in this case, frame is failed. So frame should be the first part that fails in this structure. That's the whole concept behind capacity protection. Later on when we discuss steel, we will steel design, we will revisit this idea. And in concrete, like a concrete is like sometimes even more difficult to fully understand what the code is asking us. But if you keep on assuming this chain and assuming that you are really protecting the brittle part of load path, then you understand it. Not sometimes really difficult to follow exactly what the code says, but that's the idea behind it. So modern design philosophy in summary, for like comparing two frame designs. Frame design A and frame design B both have the same stiffness. Didn't show this to. No, so but then in terms of the load displacement, they might even have the same stiffness. Elastic force would be the same for both a structure, and frame A has greater design capacity than frame B. Frame A sustains greater static load, such as wind load. So let me remember what happens here. Frame A yields later, like at a greater load than frame B, and elastic force would be the same in both frames, both result in the same elastic forces. And frame A has a larger capacity than frame B. Therefore, like when you design for wind, you assume that frame A is stronger than frame B. I know something maybe I wanted to show an example. No, maybe the slides mixed up here. Basically, okay, maybe one slide dropped out. When I make the PDF, I can look at it. So here, yeah, the intention was to show that sometimes you have a stronger structure, which with a larger capacity, which is counterproductive in earthquake design. And frame A is a stronger frame with more capacity, but it fails during earthquake because the connection capacity and the foundation capacity is smaller than the frame capacity. And so the foundation and the connection, they are not capacity protected. Therefore, you will have a collapse during earthquake because this brittle part of the load path, they will collapse sooner than the ductile part of the load path, which is the frame. And for frame B, the capacity protection is like dictated, like it's a proper earthquake design, although it's weaker. And the frame capacity is lower than the foundation capacity or diaphragm frame capacity. Therefore, in the case of frame B, the structure will properly yield during earthquake and you won't have a catastrophic collapse. So maybe the slide slightly switched and we'll look at it one more time, but that's the whole thing that we are trying to prove here. In earthquake, a stronger in classic term doesn't mean better. The capacity protection is more important, like keeping everything else the same, meaning the frame foundation connection capacity the same, the diaphragm capacity is the same, foundation capacity the same, everything remains the same. However, one parameter changes. In one case, the frame is too strong, and in the other case, the frame is strong enough. In the case that the frame is too strong and we don't have capacity protection, therefore we will have a brittle failure. In the case where the frame is appropriately designed and it's weaker than everything else, or is the weak link of the design, the yielding will happen, and therefore everything else is protected. And say during an earthquake, the residents will notice large of displacements, but no collapse. So that's what I was trying to show here. Maybe I can adjust it for next year. They basically we always like to have fuses. So in this case, the fuse or the weak link is this smaller part of the bracing. That's a smart decision. And similarly, before every other brittle part of the structure fails, these fuses yield and they will cause a lot of displacement and in a way dissipate energy, both dissipate energy and at the same time safeguard the safety. So this could be frame B where you have a weak link and the capacity has decreased and therefore it's a good design. Frame A could have been the same bracing without the fuses. So assume that these two narrower weak links are not there and you have the main member going throughout. It's basically a stronger in a way, like in the way classical structural engineering or static structural engineer would think. The structure is stronger, but it's not safer because we don't have the what we showed here in the previous picture. So the structure with fuse was less strong. However, it showed good ductile behavior. A structure that bracing, if the bracing doesn't have fuse, it's stronger, but it means that there is no fuse. And in this case, as soon as the connection between diaphragm and frame fails, everything will fall apart. So that's the benefit of weakness in a way in earthquake design and capacity protection. So I don't want to say overemphasize weakness. The benefit here is the capacity protection because everything else is stronger than the frame. So that's why frame B is a good earthquake design. So frame A could have the same bracing without fuses. That's what I said, like frame A would be stronger, but not beneficial. Frame A and frame B would have almost the same stiffness because this is very small to affect the stiffness. So both the structures will have the same stiffness. Frame A would have more strength for lateral load. But however, frame A would have greater design capacity without fuses, and it's a poorer earthquake design. Re-emphasizing the same fact, frame B would act as the weak link. So frame B has the capacity to dissipate energy and the load path will not break because it will elongate, but it will not collapse. On the other hand, frame A would not be the weak link. The energy dissipation will not happen. And part of the load path will be broken because the connections, diaphragm frame connection will fail and therefore, and it's a brittle failure, so it will suddenly collapse. Frame A collapses during a much smaller earthquake event. But this underline is interesting. So frame A satisfies the code. So that's an alarming issue that when you design based on National Building Code of Canada or ASC 7, etc., frame A would be a pass. So everything will be okay. So you need your, in a way, be aware that frame A will pass, everything will be okay, all the capacities will be check marked as okay, but frame A doesn't have that capacity protection feature. So you need to, yeah, like learn a little bit more than the code. That's to emphasize. General test to determine the weakness link is pushover analysis. Yeah, like that's one benefit of pushover analysis, even without using it for design. You just estimate the lateral load and push the structure, and you're not even concerned with determining the displacement capacity. All you want to know is that your weakest link is the first one to yield. So if you only use pushover analysis to make confident your weakest link is what you really want to be the weakest link, that's a very good use of pushover analysis. The earthquake engineer prefers the weakest link to be the ductile frame. So a good earthquake engineer wants they will design frame B because frame B is weaker than any other portion of the load path. So basically, yeah, next time I reorganize it, put this slide first to introduce and then go through the curves. All right, yeah, so that was most interesting in a way part of our discussion. Hopefully I also presented it in a interesting and exciting way. If there's any question, let me know. Otherwise, we should jump on the other next topic, which is the secondary structures. I'll give you about 1 minute. Let me open this. Non-structural elements. I'm calling it secondary structure, but in most codes nowadays they call it non-structural because they are not part of the primary structure. Still chance for questions. Already, let's see what we have here. So this discussion will be on non-structural elements. First, introduce what we call non-structural elements. Non-structural elements are not intended to resist seismic force other than those resulting from their own mass. So it's not part of, basically it's not part of the load path that we kept on emphasizing, that primary structural members or structural members are really the ones that are part of the load path from roof to ground for vertical or for lateral or both. But non-structural is a member in most general terms, something sitting in your building in a way, like my desk. It's non-structural, so it's not part of the load path. And however, it should like hold down to its own weight, and during earthquake shouldn't fly out. Or like my shelf is a better representative because we are worried that the shelf will fall off. And because I'm a structural engineer, I made sure all my shelves are connected to the wall. And I know that a lot of people may forget about it, but then I said, oh, I'm the structural engineer, so I should be the one who would tie them to the wall. So you guys should do the same because you are being, you're going to be the engineers. So you do it for yourself. Just shelves are important, they may fall off on you, or maybe they will just clog the way and you cannot leave the building after an earthquake. Architects and mechanical or electrical engineers are primarily responsible for non-structural elements. That's mostly related to them. There are three groups of non-structural elements, most importantly, besides the furniture, probably. Architectural elements such as cladding panels, ceilings, glazing, and the partition walls. And then there are some mechanical and electrical equipment like elevators, air conditioning, boilers, and plumbings. And building content such as bookcases, office equipment, refrigerators, and everything else a building contains. Seismic performance of non-structural elements. They pose a danger to people both within and adjacent to the perimeters of the building. Yes, it's possible that some stuff just fall off from a building. So we, structural engineers, have designed a nice tactile structure. It doesn't fall off, doesn't collapse. People can run away, but however, something fall off from the building, from the upper floors of the building, and just hit somebody on the street. So that's a life safety issue. So there is also very important economic reason, because the non-structural elements, they make up a large portion of the cost of a structure. That's a huge portion. Yeah, here I have noted 85%. So yeah, they are expensive. So cost of the non-structural elements can be up to 85%. So it's a little bit, at least for me, it's non-trivial, but they are also costly. However, actually, generally, they are costly. The building a building is costly, and both structural members and structural members, they have been important. However, nowadays, land is super expensive, so it overshadows everything else. And yeah, so let's say third reason here we mentioned likelihood of non-structural elements damaging the primary structure of a building to such an extent as to cause partial collapse. So again, you have designed your building primary structural members excellent in an excellent way, but what we call non-structural element added by architect or mechanical engineer hits the primary structure and damages the primary structure. That's also a third risk. So there is it can endanger people, they can endanger people, they can be costly to replace, and they can even hit the structural members or damage them. So we will see some occasions. So the effect of the non-structural elements. Then when we want to discuss the non-structural elements, we should consider that they are at an elevation and therefore they are seeing like a higher acceleration than the base. We will see that how the code has accounted for that. And basically, when you are busy designing your structure, you will look at the ground level acceleration or its characteristics, like the spectral design spectra that the code has provided to you. However, say going to the roof, the accelerations over there are like sometimes they are a lot higher. Like here it has shown 2 ice just schematically, but it could be like 5 times or 6 times. So they could be huge, like the acceleration at the roof level. If you do a modeling or analysis or other types of estimation, they could be huge. So air condition or whatever equipment that is sitting here at the roof level, it will see lots of acceleration and it might easily fly off. So that issue should be in mind when you are trying to be a structural engineer who designs the connection of a non-structural member. Also, drifting is very important. Sometimes the partitions are sometimes non-structural. They are not part of the, most of the time, they are not part of the primary structure. Say for those partitions, these deformations will damage them, which is mostly because of the interstory drift and even other members or your shelf or whatever. Because of this drift, they might get damaged rather than only because of acceleration. Acceleration will put a lot of force on them, but the drift really will dictate a new shape, which maybe the partition cannot take it and it will be damaged because of that. So a few important parts of the non-structural parts of the building. One of them is the infill walls. Comparison of rooftop acceleration of a bare or open frame with an infill frame. Infill frame has short primary period of vibration and higher acceleration. So that's something that structural engineers should be generally aware of, because sometimes any one of us just naively say, this is my building with primary members, and I have estimated, I have used a computer model. I mean, in this case, computer models could be more dangerous. Let's say dangerous or misleading, because you quickly build up a frame model in SAP 2000, and then you estimate the period of your structure using different types of solutions, or even by direct modeling. You shake the base, you will read the acceleration on top. So the shortcoming and the reason that it's misleading is that practically some, say, brick infill will be the walls of this building, and those brick infills, they make the structure a lot stiffer. Therefore, because the structure is stiffer, the period increases. So your estimate of period was misleading. And also the roof level acceleration will have very different response. And based on, if you remember what we just discussed about the response spectrum and design response spectrum, when the period is shorter, the response is higher. So you won't be surprised to see the maximum accelerations at the roof level are higher than our too naive modeling here. So that's why sometimes, yeah, like don't quickly jump into model. Say maybe the code even gives you a better estimate of period than a naive model, or somehow we should account for additional stiffness here. I mean, you can, I mean, you guys will find a way to do that, make everything stiffer so that you get a closer period comparing with the code period. But be aware of that, that this could be naive and misleading. So what happens during an earthquake? What are the damages that will happen? Again, in a bare frame, the building just deforms easily. That's the effect of deformation. Remember that we said there are two effects onto the nanostructural members, one caused by deformation, one by acceleration. And in case of infill, that completely filled this frame, the effect of displacement is greater because this is like completely constrained. Therefore, when it's under lots of compression in this direction and tension in the other direction, cracks will happen. And this is a real case, which is from Taiwan. So in Taiwan earthquake in 1999, that is a picture from there. And as you see, cracks has happened in the infill, and there's a danger that it will fall off onto the people or even car, etc., which is economic damage. So when the bare frame deflects, the stiffness of the, so it moves somewhat freely, but the masonry infill prevents movement. A diagonal compression strut forms together with a diagonal tension crack caused by elongation along the other direction, as shown here. And this is a real picture that could be dangerous to life or property. Here we have this. Here we have a section to 2 floors and an infill wall. So we have the infill wall here and 2 floors. Out of plane forces act on the infill, which spans between the floors. So in the previous slide, we showed the in-plane dangers that causes the cracks. In this picture, we are showing out of plane dangers that might cause the whole wall to fall off on the floor, or even somewhat more dangerously fall off onto the sidewalk or something. So this has happened. Infill wall damage is likely to cause a structural damage, so they may hit the primary members of the structure and damage them, and damage to the tops of several columns due to infill wall compressive strut. So I think if we carefully look here, you see that some of the concrete members are damaged because of the pressure they sustained from the infill wall. So I think we mentioned 3 issues with nanostructural. One was economic, one was that this wall falls off on people or sidewalk, etc., causes even endangers life. And we also mentioned that maybe they damaged the primary structure, which was the primary concern of us, the structural engineers. So although we said, or I quoted the book that said mainly is the responsibility of architects, but we should be very, very aware of that, or scared by that, that my structure is being damaged by a partition or infill wall. So that's an example from 1985 Mexico earthquake. Study the other issues. They may cause losing the symmetry. So again, the structural engineer has considered a very symmetric design shown by A, symmetrical frame building with center of rotation and center of mass being at the same location, which is our ideal and makes our building regular, and it's more easy to design it. So we do the design. However, for architectural reasons, there will be a stiff infill wall here. And that's what our, like, the naive structural engineer has overlooked. So because this infill wall is very stiff, the center of stiffness or center of rotation has really switched to the right, and therefore the central rotation is here. And when earthquake happens, the whole building twists while when the engineer was designing the building, they assumed that there is no twist, there is no irregularity, but practically it was irregular and it was twisting, which would have needed at least more careful design of connections and accounting for rotation. So that's again what a structural engineer should be aware of. So what are the remedies? Remedy number one, confined masonry construction that is fully integrated with the structural frame. So in a way, it's saying that let's design that masonry construction, consider it to be primary structure, reinforce it, and account for it in your structural design. And the drawback is that numerous architecturally restrictive criteria that apply to the confined masonry construction. I guess like if there are like opening and then the design will become more and more difficult if there are some restrictions, architectural restrictions in terms of opening or the thickness, or you cannot put reinforcing in there. So it will make your life miserable. So it will be very difficult to go that path and make it primary structure. Remedy number two, provide a very stiff primary structure. So to start with, one might think that, okay, let's have my structure so stiff that this infill doesn't really increase the stiffness. The structure is so stiff that the stiffness doesn't really change. But only concrete can provide, or a concrete shear wall can provide so much stiffness that the masonry stiffness is comparable and it won't be affecting everything. Like if the stiffness of this structure is provided by some concrete shear walls, adding masonry shear wall doesn't change the stiffness characteristics of the structure as much as it did here. But yeah, like with a steel, it doesn't work. Remedy number three, which is the better one, is, or I would think it's the better one, is separate the infill wall from primary structure. Like the gaps are provided here. That's mostly remedy number three, gaps. If possible, to provide gaps on the sides and on the top, then they don't really hit each other. They don't really act together. However, the drawback is that the infill wall becomes extremely vulnerable to out-of-plane forces besides architectural challenges. So maybe the architect doesn't even agree with that in a way, in simple terms. But even structurally, now you have a standalone heavy wall here that might fall off under its own weight or by a small earthquake. So let's see what has happened in real life design. This is an office building in Pisco, Peru. And Pisco reminds me the name of a liquor, but yeah, so it's in Peru. And yeah, infill walls separated partial height infill in a moment frame. So it didn't go all the way in the elevation. due to the low height of the infill, its out of plane inertial forces can be restricted by two small RC column. So this wall has its own structure. It has its own RC column that prevents its falling out of plane. So and in this section, I'm not really giving you a very general solution that applies everywhere, but I'm only telling you that there is a challenge and you should be aware of that. And like other people, if you investigate, you will see that there have been some solutions here and there. So you should be mostly be aware of the challenge with infill wall nanostructural members. So another the case, let's call them case study because I think we are covering everything, but another case study is on the staircases. So staircases can act as like not designed braces. So they have a bracing action of a stairs connected to the structure would cause damage to the stair support structure and the primary structure. Say we have a single flight stairs as shown in this elevation view. What is the issue here? Like stairs, they are not like in this case, they are non-structural, so they are not really designed to be ductile. We have a brittle, non-ductile bracing unwanted by the structural engineer. The structural engineer didn't really design for it, but they will be under a lot of compression during earthquake. These are earthquake loads, and therefore they become compression struts, and maybe they fail only because of that. So this is a picture, I don't know which earthquake, I didn't note it down, but the stairs, exactly because of that reason, they are broken. So we should be aware of that. Yeah, I mean, this is not a solution to like every similar challenge, but we can think about that how to prevent the stairs from acting like bracing, and let's like separate them. Let's have a roller here in terms of a structural analysis that really prevents this member from absorbing lateral force, because the lateral force is separately designed for by the engineer. Say a plastic sheet or equivalent is used to form a sliding plane. So you have a sliding joint here, and if the sliding joint was applied here, these stairs couldn't really take load because it slides. Basically, these issues would be overcome. Another remedy would be a stair separation. So you see that this part is really hanging here. Therefore, again, it gives it room for movement. For us as structural engineers, we know that like because this member is hanging from here, it cannot really take lateral load. If it pushes to the side, it just displaces because this in a very hinged member, it can take vertical load, but it cannot take lateral load. So this is a combination of these two, and like this structure won't be able to take lateral load because it will just move sideways. This is the idealized notion, or for us engineers, it's more like a design or modeling simplification, idealization. Upper flight fixed at end and landing height. So the idea of the landing here, if you think in terms of load path, if a loads come here, it cannot really go through this because it only causes a lot of deflection here and it cannot hold down to anything. So the staircase won't act as in a way lateral force resisting system, and we don't want it to be. I have taken a lot of these pictures from a book called but it's like earthquake design for architects. So in simple terms, they are showing pictures, but it's super beneficial to us to have this visualization, and that's something that probably we understand better than most architects, why this is working. Elements of structures and structural components and equipment, jumping into our code and more rigorous equations that us engineers like better. The code tries to provide a simple equation. That's what MVCC does. Like, instead of even more rigorous computer models, they provide good estimate of the loads that we can use to design, and then they give limitations on when this solution could be used. So for the force that could be used for non-structural members, the code provides an equation shown here. We go through the parameters of this equation. This should be familiar to you because this is like the spectral response at 0.2 seconds. So you should be like gradually be able to at least quickly read the equation, and then the notions are described further here. Importance factor, you should be able to quickly guess what this is a new factor that is explained here, mostly to account for the amplifications. Remember that we said the base spectra, which is mostly this part, is not the same as the roof spectra. Therefore, the code has created or estimated amplifications to account for that. And then the weight of the non-structural component. So we want to know if we want to go by design and design anchoring connection for my shelf here on whichever floor of a building. The code decides to tries to give us a good tool, simplified tool. And simplified tools are, we repeatedly said, they have two benefits. Benefit number one is that they are simple. Benefit number two, which is almost the same, is that, okay, the young people like to use more advanced tools. However, I should be able to supervise and check and verify. Therefore, they use more complicated tool. I use my simple solution, then I compare to make sure that they have not gone sideways. So those are the benefits of knowing about the simpler solutions that the code has provided based on experiment and experience. So basically, except as provided in other sections, elements and components of building in this section. So section 418 subpart 18 is on non-structural members. It's good to remember. And their connections to the structure shall be designed to accommodate the building deflections calculated in accordance with other articles. So we discussed that sometimes the non-structural members damage only because of the drift. So there's a drift force that because the drifts happen at every floor, maybe whatever anchor I put on my shelf here, that you guys can see it on this side, only because of the drift of the building, this shelf cannot sustain it and it will break down. So we should be aware of the deflections. And we also talked about the infill, which was the extreme case where the deformations will cause damage. And also we talked about acceleration, and acceleration translates into the force. And the code tries to give us a good estimate of the acceleration / force at every level, any level of the building by this equation. So this equation is more about acceleration and force. And deflection is the deflection of the whole building. And we already discussed how to estimate deflection and drift. So going through this equation, S at point 2 is the design spectral acceleration at a period of 0.2 second, which you read from your design spectral acceleration. Remember, you get it from website. Importance factor is importance factor of the building. Saying we discussed some like there's regular everyday buildings, and there are like barns which are lower importance, and there are major bridges and hospitals which are more important. So you can use tables from the code. Now this amplification again going there, just so that it makes sense to you. No. Yeah, general amplification. So the amplification factor is about the fact that at the base, the acceleration goes into, say, 1g. However, at the roof, the acceleration goes more than 2g. So if you want to schematically remember this issue, that's what we are trying to estimate. So that's all we are doing with SP, and the code is helping us to do it more quickly estimated. SP has a few factors inside. CP, which is element or component factor, there's a table for that, which is mostly related to stiffness. AR, element or component force amplification factor, there's a table for that, meaning that how much the, like within the member, within the shelf itself, how much amplification I get. Then there is AX, height factor. That means how much amplification I get because I'm not at the ground level, I'm at 5th floor. So AX gives a simple estimate on how much increase I should account for because I'm at the elevation. And again, similar concept as we previously discussed, there is a reduction factor because, say, the anchoring I have used to connect my shelf to the wall has ductility, maybe it's steel, whatever, and it has ductility. So because of that ductility, same concept that we reviewed, we can reduce the force. And the WP is the weight. So almost similar concept as what we had before. However, here we have a amplification factor, and there's a limit. The max and min determined by the code. Be aware of those max and mins. And the code is really trying to help us get a quick estimate of the force to design anchoring of the equipment. I think, yeah, we can stay here. I like that you guys really think about this. But until next week, I'm here to answer a few questions, if any. As we said, the deadline has extended. I should remember that I gave the promise to give you some comments by Monday, and then Monday 8th, and then you will have until Monday 15 to submit your report. That's important dates for you. Yeah, hopefully everybody enjoys the weekend. I will chat with you on Tuesday. Take care. And yeah, I can close this off, but yeah, I'm here to answer. Thank you. Sure.